Hello everyone and welcome to the fourth lecture of solid-state chemistry, in which we are going to talk about magnetism and what makes a magnetic material. The lecture is going to be divided in 3 different videos. All together they make the content of the week, so please follow them in order, but follow them at your own pace. We are going to start with the principle of magnetism, so where does magnetism actually come from and how does it correlate with what you think about magnetism in general normal life. How do we go from the concept of physical magnetism into the magnetism possible behaviors that you can have, all the transitions that are correlated with that, is going to be in the second video. And then in the third video, we're going to see the features of materials that you actually call magnets in like usual common speech. You can follow the progress of the video in the bar on top, and there is a single feedback-free document in our Canvas page in which you can leave any comments or flags or things that really spook you in particular for our discussion live when the time comes. So magnetism as an effect, as it is not exactly a new concept. It's something that humans have experienced since the ancient times. It's something that we have seen happening, but it took a long while to be systematized. So in general, we record and think about magnetism as the possibility of usually something that we think about as metallic to attract other metals and stuff like that, but it's not necessarily a metal as we think about it. The original magnetic material is usually recorded as iron 304, which has the name of magnetite for clear purposes, and it's a bit of a chicken and an egg situation of do we call it magnetism because it comes from magnetite? Kind of yes. And it was a type of it's a type of iron 304 oxide that is not just the oxide, is naturally magnetized. So in ancient times, this was the only occurrence of a material that could actually be magnetic. You had no way to make it, you could just spot it. But the fact that it has these general behaviors actually chained into a lot of peculiar realizations, like the fact that this lodestone material will randomly apparently orient itself in a very specific direction on Earth that we now know it is the direction of the magnetic field of Earth, so it will point towards the magnetic north, and you can use it for a compass to orient yourself around. None of this business was in any way connected to atoms, electrons, the actual source of this thing before the 1800. But the 1800 is the age of electromagnetism, and at that point we kind of understand not only the mechanics, but after that the quantum mechanics of how this thing comes to be. So how do we actually unpack magnetism from the quantum mechanics? Because the quantum mechanics is going to be here. We're not going to go in depth in there, but the magnetic phenomena are for the most part caused by exactly these quantum mechanical behaviors of electrons. There is no way to unchain them. They come together. So basically the thing is that nuclei in themselves have a magnetic moment. They contribute to the magnetism, but usually the magnetism of the nucleus of an atom is way less, like orders of magnitude lower than anything that you can have from the electrons. So usually you, if you want to approach what happens in terms of magnetism in your material, you approach it from the point of view of the electrons. So from basic quantum mechanics, which is also the one that you use in chemistry, you might recall that to figure out what is the energetics of your electrons, you usually use a series of quantum numbers that are associated with the orbitals. So they determine these things are correlated with the forms of the Schrödinger equation when you actually want to solve it, but it can be solved only for the hydrogen atoms. So our N and our L are the principal quantum number and the angular momentum quantum number. Then you have ML, that is the magnetic quantum number, and MS, which is the spin. Now, these things are the things that when you sum them up, when you consider all of them together, they determine the properties of a specific electron in a specific atoms according to the whole situation. For most elements, you're like, okay, we have the bulk thing that you can consider all together because everything is filled and paired, and then you are concerned mostly about what is going on in the valence shell, so in the last possible layer of occupied orbitals. So basically, apart from the point of the energies, because the Aufbau principle and the Madelung's rule will determine in which order the N and the L shells are filled, so you go up in which order you go following this type of thing. So the N determines the energy of the electron level, L determines the magnitude of the orbital momentum. So there is some motion going on in the orbitals, you account for that like that. And that basically correlates with which level are you in. Is this a 3D, 4D, 2S, 1S? These are the numbers. You know them, you just maybe don't think about them very often. And you fill them up in this order. But then when you get to the ML and the MS, the issue there is that you will have several filled shell and the partially filled shell, right? So which one of the available orbitals are filled is ML, and in which spin state you leave the shell is the MS. So for an isolated atom, you use the Hans rule to sort these things out. We used it already, but we're going to refresh it. Basically, you determine the fact that you need to fill in alignment. You try to fill as many orbitals as possible. You maximize the orbital angular momentum, and you tend to first align before you anti-align the electrons. Now, if we try this thing not with a common atom, but with an atom that will actually have a partially filled cell, like an atom that many of you might have never seen, but we're going to discuss it later if you want, praseodymium, okay? Number 59 of this whole business, right? Now, in praseodymium, you have electrons in the outer F4 shell. So L is equal to 3, and ML goes from minus L to plus L. So from minus 3 to plus 3, you have 7 possible levels. MS can only assume 2 numbers, plus half, minus half. That's the only thing you can do. So where are these 7 electrons? You follow the usual rules. So you go as far off in L as possible. So you try to maximize L, and you want to have the spins aligned. So going from minus 3 to plus 3, then you start from 3 to 1 of the levels, and you try to align the spins because there is plenty of space. So you have a total spin that is the sum of 3 spin plus spin plus 1/2 going around, so 1/2, 2 halves, 3 halves, and the total L is the multiplication. So 3 per 2 per 1, L is equal to 6. So that's the total thing. Now, how the spin and the orbital angular momentum align with each other, because you basically have an arrow of vector in one direction and an arrow in another direction. How do they align with each other? This is called the spin-orbit coupling effect. This gives you the total angular momentum of your electron by combining the spin and the orbit. And you have it with the total number L plus the total number S. So in this specific case, your total angular contribution is 6. Your shell is less than half full. So this plus and minus becomes a minus. So you have 6 minus 3/2. Your total angular momentum J for this specific material is 9/2. So this is the thing that you have going around. By nature of having these particular atoms with these particular energy levels and this balance, this is your final angular momentum that you can actually bring towards magnetic effects. Magnetic properties are usually expressed in terms of this magnetic moment mu, we call it, because it relates directly to how many unpaired electrons do you have in your atoms to bring towards the specific stuff. So as we saw before, any magnetic property comes from electron spin and electron orbital motion, right? And usually prevalent in D and F type of atoms, just because they are the one that can have an half full shell. You don't have that flexibility on quantum numbers unless you have this type of stuff. But if we want a unit to try to express this thing, we can just derive it from the fact that in general you can imagine that every atom will have at least electrons in an orbit around a nucleus, right? So you have an electron that goes around, like this is a very classic representation, but it's an electron that goes around in an orbit of radius r around a nucleus with velocity d. Super classic, but it doesn't mean that it doesn't work. So if this electron has a charge, as a mass of the mass of the electron, the charge minus c, it goes around in this orbit, that in reality we know it's an orbital, we know that an orbital is not just one possible trajectory, but classically speaking, this thing should generate a current that reflects the orbital period. So as it goes around with this velocity v, you have a current that is dependent on the electron charge and the 2 pi r type of business here. Now, how do we correlate this thing to a bigger picture? By knowing that at the ground state, the angular momentum and this thing, h bar, which is the Planck constant, need to be equal. So if they need to be equal, then the momentum that you generate by having this type of current going around must be equal to this sort of weird unit, but it needs to be correlated like this. Now, these are a series of constants at the end of the day. Like, since you know what is your deal going on here, the Planck constant is a constant, the mass of the electron is a constant. If you know this, then you can derive a specific unit of how much magnetism do you have going around. This is called the Bohr magneton. So if you want to quantify how much magnetism are you having because of your unpaired electron, you go by Bohr magneton. So instead of thinking about all these constants that give you this sort of current per square meters, you just go with a Bohr magneton and you call it a day. Now, the spin of the electron that you have here, you need to consider the rotation on itself and the angular momentum that goes around. So instead of considering just the spin, you try to put these two units in this geomagnetic relation J. So for a general system, your magnetic moment mu will be correlated with the spin, the total spin, like this. Now for a single electron, imagine you have a single unpaired electron in this whole business, you can have spin half. Your geomagnetic ratio, you can consider it as around 2, because in normal situation it's a constant of around 2. At that point, if you calculate this whole business, just plug in a number here, it comes out as 1.73 Bohr magneton, so you use it as your unit of magnetic moment generated by this whole thing. Depending on how many unpaired electrons do you have, this thing should be propagated. So usually for an ion that possesses n unpaired electrons, the magnetic moment is n Bohr magneton. But this is a very blanket statement, so this is something that will bring you with manganese 2 plus is 5 Bohr magneton, but iron 3 plus is also 5 Bohr magneton. It's very easy to quantify, it's a blanket statement, but usually this value underestimates the real value, because the real value needs, especially if you have multiple unpaired electrons, it needs a consideration of the orbital moment together with the magnetic moment. So depending on how you calculate this, so if you calculate it as a single sum of the magnetic atoms, or with the spin orbit coupling, you can see that depending on which ion you are considering, with how many unpaired electrons in which possible states of angular momentum, you will find yourself with values that are closer to the observed values depending on this thing. So for instance, for vanadium 4 plus, considering this like a single, just with the sum of the spin, the total spin of your unpaired electrons is actually very close to reality. But when you go for stuff like cobalt 2 plus, if you just consider the spin total number, it's severely underestimated in comparison to the spin orbit type of calculation, in which the spin orbit is actually close to the real observed value. Now, these real observed values, how can we possibly get them out? Now, to get them out, inevitably you need a measurement, and to have a measurement, at the end of the day, you need to consider how does your substance react to a magnetic field, because that's magnetism, that's the core of a magnetism. If you place your substance in a magnetic field, so you have a magnetic field that is going on, your substance is inside, you want to know the density of the flux that is inside. So how magnetizable your substance is, the density of the line of force inside, which is a magnetic induction, will depend on not only the external magnetic field applied, but also by the susceptibility, basically, of your sample. So this thing is correlated usually with an induction that is based on the magnetic field. So if you use mu0 as the permeability of the free space, so you have normal free space, how do the line of field of magnetic force pass through, and a part that is all derived by the sample. This value m is the magnetization or the magnetic moment of the sample. That's the thing that is telling you, okay, this is my contribution to this business. So the magnetization of the sample per magnetic field is what we call the susceptibility. So what is, depending on how much magnetic field do I add, how does the sample respond? So is this ratio over here? By nature of being a ratio, it's technically speaking unitless. It can be correlated to the permeability, so the permeability of your sample relative to the vacuum. So the relative permeability is 1 plus the susceptibility, if you solve this thing by the susceptibility. All of this thing is unitless, but you need to remember that magnetism has been around for a long while, so you will often find yourself with a lot of weird, not SI units that are still regarded as normal units for scientists that actually work in the field. It really depends on how you were trained, what units do you like to use the most. So even in this lecture, you're going to see different units flying around. The different magnetic behaviors, that the reason we like this thing is that depending on the value of the susceptibility, you can distinguish a series of different magnetic behavior and their behavior with temperature and field, and stuff like that. So it gives you a way to quantify how is your substance actually reacting to the magnetic field. Now, this is a very important point because this can cause a lot of confusion. So when we talk about a substance reacting to the magnetic field, we're really harvesting the power of the solid state once again, because if you can have this magnetic effect with an isolated atom or an atom in a molecule, and they're still relevant. You have plenty of spectroscopy, as a lot of you might know, that acts based on the magnetic effect of your atom in a sort of isolated or free state. But it's different when you go into the solid state, because the solid state forces a series of atoms into interaction. And that's the key point that we've been using a lot throughout all the previous lectures. In this case, it's going to be the same. So instead of having free magnetic atoms going around, you have a series of magnetic atoms forced into interaction with each other, and when they are placed in the magnetic field, they all need to react in the same way, possibly also knowing that they are going to be arranged in a lattice. So a coordination complex of cobalt, which in itself is a magnetic atom because it has a partially filled shell and it will have magnetic numbers that can lead you to the Bohr magneton, is different from having cobalt into a structure, for instance. So this is a real paper that I even put here, in which they comment on the magnetic structure of this specific material with cobalt, and they comment also on the fact that only one of their cobalt has the unpaired electrons to be magnetic. The other one actually ends up having all paired electrons, so it doesn't have a possible magnetic moment, and they are trapped in this structure. So when we consider them, we consider them all together, and this can give rise to very, very funky effects. But depending on which material do you have, the funky effects might very well vary. So which type of magnetism do we have? The type of magnetism are always related in terms of the response to an external magnetic field. In the same way we were commenting the susceptibility, so we can contextualize the susceptibility based on the behavior that you see against an external magnetic field. So you have your external magnetic field, you're imposing it, you put your material in between. If your material is diamagnetic, there will be a slight repulsion of the magnetic field that you're imposed from the material. So the material, instead of having a very even way to pass through, so if this were to be vacuum, the line of force of your external magnetic field should stay perfectly steady. When it passes through your material, the line of force, if your material is diamagnetic, will open up. So the density inside of the material will be lower than the one on the outside or the one of the vacuum. Diamagnetism, in general, it's an effect that every substance tends to have, because it's a reaction of the fact that you have this series of clouds of electrons that like to go in the way they like to go. When you push a magnetic field through, there will be a force of alignment, a counter force of orbital motion in reaction to the application of the magnetic field. So this orbital motion generates a very small magnetic field by itself, and in the presence of the external field, this modification will give rise to a magnetic moment that opposes the magnetic field. So you slightly repulse any magnetic field that you put through the substance, meaning that your susceptibility will be very, very, very tiny, but negative. So that's the key of the thing. And a lot of substances, even substances that we know are not magnetic, water, will have a diamagnetic effect, small but negative. You can see that all these values are in terms of 10 to the minus 5. This is incredibly tiny, but still present. This is independent of temperature, independent of field. Doesn't matter how much field you put, your substance doesn't care, it will just have the same level of reaction. On the other hand, you can have paramagnetism. So if your substance is paramagnetic, in the presence of a magnetic field, the line of forces passing through the material will get concentrated. So your substance is slightly attracted through the magnetic field. It likes the magnetic field passing through, and it densifies it in comparison to the open space. So if you think about it, the theory that you have behind this whole thing is that it's called the Langevin theory. And basically you have a series of non-interacting magnetic moments. They're just free to go whenever they want. They are there, but they're just non-interacting. When you put a magnetic field passing through, these free and ready to go magnetic moments will sense a magnetic field and locally align. Now, this is not a full alignment, but they will accompany the field, and by accompanying the field, there will be a slight magnetization coming through the sample. So this is very slight shift. It's a very tiny fraction of them. Only a small fraction can go into the field direction. So regardless of how much do you put of field, you still have a very tiny amount that can go. So this is independent of field, slightly dependent on temperature, because depending on how much temperature do you put, you shake them around more and they might or might not want to follow. So at higher temperature with more thermal disorder, you just move them around, they play, and they are not bothered, so their reaction will be less at higher temperature. So this thing is the theory that we were discussing. So external magnetic field, slight reorientation. If there is more temperature chaos, then the effect is dampened. Now, this thing was based on the fact that you have a net magnetic moment of your atoms. So all of your atoms have that calculation that we did before. They give us a net magnetic moment that you can actually realign in the field. But if you don't have a partially occupied valence shell, we don't have that magnetic moment. That doesn't necessarily mean that no atom will have a paramagnetic behavior. You can see that tungsten, aluminum, lithium, sodium, which are all with no reason to be magnetic, with no partially occupied valence shell, they all have what you expect of a paramagnet, small and positive susceptibility. These things are called the polyparamagnets. Now, the trick is that the Langevin theory assumes that the electrons in the partially occupied valence shell are localized. Now, this works if you have basically your d electrons, or even more so the f electrons, because they like to keep the electrons localized. But we discussed already the effect of the bands, so this approximation might not be that good if your material is something like lithium or sodium, for which we derive nicely the full metallic band theory, with the electrons capable of moving through an alpha field band that spans the sea of electron of the whole material. So this trick is a trick that opens up because of that Fermi energy type of deal. So if you imagine a 0 Kelvin, so even with no temperature effect, you have the highest occupied level of energy, that is the Fermi energy. At that point, if instead of just thinking about the band, you also subdivide the band in terms of spin up, spin down, this will be your full band, but then you have one part of the band spin up, one part of the band spin down. For the electrons that are very close to the Fermi energy, it's easy to jump to unoccupied levels, which will allow to basically break the Pauli rule of wanting to pair the electrons. So if you were to impose a magnetic field in a certain direction, in this case, let's go direction down, there will be a significant amount of electrons that, rather than going to higher energy because they will be opposed to the direction of the field, which will bring them to a higher energetic state, will prefer to flip the spin and just go in the other direction. So you have a shift of bands occupation that is exactly dependent on how much magnetic field you're putting. So under magnetic field there is a very small but still relevant magnetization developing. This is an effect of deciding to shift the occupancy at the near the edge of the Fermi level. So this paramagnetism usually is for magnetic moments of atoms with a partially occupied valence shell. Pauli paramagnetism, it's what happens when you need to consider band theory into this whole business. Two additional effects are ferromagnetism and antiferromagnetism, and some of these are the ones that you actually recognize as a magnetic behavior. So this behavior comes when you actually have atoms with magnetic moments that, instead of being randomized, as we were discussing in the paramagnetism case, are actually aligned with each other. So in ferromagnetism you have this alignment all up, so they're all in the same direction. This means that the total magnetic moment is definitely higher than zero, because whereas in paramagnetism the total magnetic moment is null because they are not all aligned in the same direction, they tend to cancel each other out, there is no real magnetism of the whole material. If your material is ferromagnetic, it means that everything is going in the same direction and you can have a total magnetic moment that is higher than zero. The magnetic flux in this material is incredibly higher than what you have on the outside, so they are really attracted by the magnetic field. They densify the magnetic field and accompany it. So the susceptibility of this material is way, way, way higher than zero. So for instance, iron has 5 to 10 to the 3. If you remember paramagnetism positive in 10 to the minus 5, this is a real susceptibility behavior. This thing is field dependent, because depending on how much field you actually feel a different effect, and decreases with temperature. In antiferromagnetism, the alignment is anti-parallel, so the total magnetic moment that you can get from this material is zero, because all the moments will painstakingly cancel each other out. If there is one up, there will be one of the same magnitude down. Total magnetic moment, zero. The flux inside of the material is slightly more than it would be in the vacuum, but really, really tiny effect. So this is a bit higher than paramagnetic behavior, but still incredibly low. So 0 or 10 to the minus 2, but it's low. So it's either completely null or very, very tiny. It increases with temperature, can be very weakly dependent on field, just because some stuff you can force to go in the other direction, but for the most part you don't go in the other direction. Now this is the outline of how do you get magnetic moments and how magnetic moments can actually behave in your material. To see ordering, disordering, temperature effect and field effect, we're going to go to the next video.